Good evening, students. So this is going to be the last class on electrochemistry. So before starting today's class, let's look up into what we have learned from previous class. So this class was mainly based on strong and weak electrolytes and also their variation, the variation of their molar conductivity on dilution. And it was different for strong electrolytes and weak electrolytes. So we studied two different theories which would explain the change in the molar conductivity during dilution for each of them. So in case of strong electrolytes, we had Debye-Huckel-Onsager theory for its explanation, while for weak electrolytes, we used Arrhenius theory or Ostwald's dilution law. So as per Arrhenius theory, we have learned why do we get an exponentially increasing graph on dilution. Okay, so the equation was alpha, which is degree of dissociation, directly proportional to 1 by root c or inversely proportional to root c. So because of this relation, we are getting a graph like this. In case of strong electrolytes, that is in Debye-Huckel-Onsager theory, we learned there were two mainly contributing effects, which was asymmetric effect and electrophoretic effect. And also the equation was lambda m equal to lambda 0 m minus b root c. Here lambda 0 m is molar conductivity at infinite dilution. We also see a linear relationship between lambda m and root c from this equation, and hence we have a straight line graph. The next thing we learned was Cauchy's law of independent migration of ions, and we told that the lambda 0 m, that is molar conductivity at infinite dilution, can be found by extrapolating the graph or the particular straight line for strong electrolytes. But in case of weak electrolytes, any extrapolation will not give you the lambda 0 m value. So Cauchy's law can be used to calculate the lambda 0 m value for weak electrolytes by using the known values from strong electrolytes. So I've learned that we will use a combination of ions to get the ions that we are required, and we'll calculate lambda 0 m value for weak electrolytes. The second application was to calculate alpha by using the equation lambda m by lambda 0 m. Now let's go to today's class. So today's class we'll have some topics which are not really connected with each other. So we're going to start with something called transport number. Transport number. So we know electrolysis, right? So in electrolysis, what is happening? We will be using electricity in order to carry out some sort of reaction, or we'll be converting electrical energy into chemical energy. So we are actually externally providing some sort of current. So what happens is during the process, the anions and cations that are formed will be carrying the current that we are giving. So anions will carry certain amount of current, and cations will carry certain another amount of current. So the amount of current carried by them is actually proportional to their mobility or their velocity. So we find that the amount of current carried, by ions, whether it is cation or anion, it is directly proportional to their speed or velocity or mobility. And we know that when their mobility is higher, what happens to their conductance or conductivity? When mobility increases, we know that their conductivity also increases. So this is directly proportional to their conductivity also. Okay, so during an electrolysis process, we are giving externally some sort of current which will be carried by the ions in the solution. And this, the amount of current carried is directly proportional to their mobility or their speed. Now let's define transport number. So transport number is defined separately for cation and for anion. Okay. And their sum will give the overall transport number. So in general, transport number is represented as T. and for cation it will be T plus, and for anion T minus. So total transport number will be sum of transport number of cation and transport number of anion. So this is one important equation. T is equal to T plus plus T minus. Now you have to define separately what is T plus and what is T minus. So transport number of cation or anion, that is transport number of any ion, is the fraction of current carried by that ion. So first let's write the definition. So transport number of any ion, transport number is actually fraction of current carried, fraction of current carried by that ion. So how will we write the equation? T, suppose I'm writing for cation, I'll use T plus. So T plus is going to be fraction of current carried by that ion. So since it is a fraction, it means the current carried by that ion will be I plus. I represents current divided by the total current. That will give you the fraction of current carried by that particular ion, here cation. But we also know that since transport number T is equal to T plus plus T minus, in similar terms we can say total I, the total current will be current carried by cation plus current carried by anion. So I can write I as I plus plus I minus. So total current carried is obviously current carried by both ions, right? There are only two ions to carry the current. So there the current carried by both of them will constitute the total current. So in terms of current, we can write it in this way. But we also know that amount of current carried by ions is directly proportional to their speed, velocity or mobility, and again that is also directly proportional to their conductivity. So the same fraction we can write in terms of speed or velocity and also in terms of conductivity. Let's see how that will be. Now T plus can also be equal to, let's represent speed as U. So U plus divided by total U. Again, total velocity or total mobility is sum of U plus and U minus. U plus plus U minus. Now let's write it in terms of conductivity also. U denotes velocity, speed as well as mobility. Okay. Now in terms of conductivity, we can represent with lambda. So lambda of plus divided by lambda. And total lambda will be lambda plus plus lambda minus, that is conductivity of both the ions. Now this is how we will be representing the transport number of cation. In same way we can represent the transport number of anion also, only a small change in the sign should be given. Okay, so we can just do the exact same thing for anions. So the changes we have to make is T plus will change to T minus and I plus will change to I minus. Similarly U plus and U minus also. So T minus is equal to I minus by I, which is again I minus by I plus plus I minus. Similarly T minus is U minus by U. That will be U minus by U plus plus U minus. Again T minus can also be equal to lambda minus by lambda, which is equal to lambda minus by lambda plus plus lambda minus. So this is how we will be writing the transport number for anions, and on the left side we have that for cations. Okay, so next we are going to learn one important parameter that is called as the ionic strength. So ionic strength, which is represented as I, can be called as the measure of total concentration of all the ions present in the solution when we consider their charge also. So ionic strength can be said as measure of concentration, total concentration of all ions in a solution while considering their charge also. Of each ion. So this is called as ionic strength. So don't worry about the definition. We'll look into the equation, which is more important for us. The equation is I is equal to half of summation over I mi into Zi square. So this is the equation for ionic strength. And let's look into what are the terms involved here. So firstly we are saying I, which is obviously ionic strength. Then we have M. So M represents Mi represents molarity of ith species. And Zi represents charge on the ith species. Okay, so these are the only two terms involved: molarity, which is concentration, and charge, all present on the ion. So ionic strength can be found by taking the product of molarity and square of charge for every ion and summing them up. Okay, this is how we'll be finding ionic strength. So this will be more clear when we do problems. We'll be doing a lot of problems on this particular thing because this is an important topic. Let's start doing the problems. So first question, calculate the ionic strength. Calculate the I value for, I'll give some different compounds with their concentration. Okay, first one is 0.01 molar NaCl. Let's look into how this should be done. Firstly, the process is just have to expand and write whatever salt or electrolyte is given to you. Expand in the sense, just write how they will ionize. This will make your steps easier. So we have Na plus Cl minus. So the charge and everything on this is very clear to you. Okay, so we one NaCl is going to produce one Na plus and one Cl minus. So if the concentration of NaCl is 0.01 molar, then obviously after ionization, since 1 mole of NaCl gives 1 mole of Na, the concentration is 0.01 for Na also. Similarly for Cl minus, the concentration is going to be the same. And what are the charge? 1 and 1 on both. So we have two ions. Firstly, that is Na plus, which has molarity or concentration of 0.01 and charge of 1. In case of Cl minus, the next ion, molarity is again, let's denote it as M1 and Z1, M2 and Z2. So M2, the concentration is 0.01 molar. Z2, the charge on Cl minus is -1. Now let's put these values into the equation we know. So the equation for ionic strength is I is equal to half into sum over I mi Zi square. That means here, since we have two ions, we will be using M1 Z1 and M2 Z2. So that will be M1 Z1 square plus M2 Z2 square. Since we have already picked out the data and written it clearly, substitution is only process left. Half into M1 0.01 into 1 square plus M2 0.01 into -1 whole square. So what will we get? Half into, this is 0.01 itself plus -1 square is 1 itself. So this one plus 0.01. That will give half into 0.01 plus 0.01, 0.02 and when you halve this, again you will be getting back 0.01 itself. So this is the ionic strength for a 0.01 molar concentrated sodium chloride solution. Now let's go to the next question. It is similar one. We have the same concentration, 0.01 molar, and the salt is CuCl2. Okay, how do we do this now? Firstly, we have to write the equation. So CuCl2 becomes Cu. The charge on Cu will be 2 plus 2 chloride ions, so 2 Cl minus. Looking at the charge, we see that copper has a +2 charge while chloride ion has a -1 charge. Okay, since there are 2 chlorine ions, don't put 2 minus, because the charge is always constant for one atom, that is -1. This 2 will be accounted for in the concentration. Do not put it in the charge. This 2 will go to concentration. Just look at this part for charge. Okay. Now the concentration is 0.01 molar here. Since 1 mole of copper chloride will give 1 mole of copper, the concentration of copper is the same, 0.01 molar. But 1 mole of copper chloride is going to give you 2 moles of Cl minus. So here the concentration is going to double, or you can write 2 into 0.01. That will be 0.02. This is how you find out the charge and the concentration. This is the main part. Rest is only substitution, which like anyone can do. So in this part, you have to identify the charge, which is only the charge at the end. At the top right corner, you can see that is the charge. So Cu2 plus, charge will be 2. 2 Cl minus, the 2 will go to concentration, not to the charge. So there should not be any other confusions here. Now let's put into the equation. We know that we don't have to separately take out the data and write every time. If this is fluent for you, then you can do it directly. So I will be half into, again 2 ions are involved. So I will write M1 Z1 square plus M2 Z2 square. That's going to be half into, M1 is molarity of the first species. If I take that as copper, 0.01 into, what is the charge? 2 square, plus M2 is Cl minus, concentration of Cl minus, so that is going to be 2 into 0.01. That will be 0.02 into the charge -1 whole square. So that will be half into 0.01 into 2 square 4 plus 0.02 into -1 square 1. That is half into 0.04 plus 0.02. That is going to be 0.06. On halving it, we'll have 0.03. So this is the ionic strength for 0.01 molar copper chloride. So now if we compare both of them, we see that it was same concentration of the salt initially. Sodium chloride and copper chloride, we took the same concentration, 0.01 molar. But the ionic strength was different because of the ionization is different. The number of ions produced on ionization is different for both of them. So let's look at one more question which is of similar concentration. But again, the number of ions produced on ionization is going to change further. So the third question is 0.01 molar of LaCl3. Okay. Again, we are going to proceed with the same way we did for the above two. Just writing LaCl3, ionizing it. La plus 3 chlorine atoms, so 3 Cl minus. So obviously, if the total charge constitution is 3 minus, so La has to go 3 plus, right? Okay, now let's go to the charge is always 3 plus here, 1 minus here. Okay, so don't take, since there are 3 chlorine atoms, don't take 3 minus for chlorine, take 1 minus, and as I told, 3 will go to the concentration part. So here it is 0.01 molar. 1 La3 plus will get 0.01 molar. 3 Cl minuses will get 3 into 0.01 molar. So this is the concentration, how it goes. Now again we are going to substitute in the main equation. So ionic strength I is equal to half into, again two species, so M1Z1 square plus M2Z2 square. So we have half into 0.01 into Z square is 3 square plus, for M2 it is 0.03, okay, into what is Z square, minus 1 whole square. That is going to be half into 3 square is 9. 9 into 0.01, you are going to get 0.09, plus minus 1 square is 1, into 0.03, you will get 0.03 itself. Finally, half into 3 plus 9 plus 3 is getting 12. So this will be 0.12, and on halving it, you will get 0.06. So this is going to be the final answer, or the ionic strength of 0.01 molar LaCl3. Okay. So these three questions, we had same concentration but different electrolytes, which on ionization is going to give different number of ions. Now, but still all of them were just one electrolyte type of solutions. Now let's see, what if we use a mixture of electrolytes or mixture of salt in a solution. So the next question is going to be, calculate the ionic strength for, or calculate I for solution containing 0.01 molar Na2SO4 and also 0.02 molar CaSO4. So sodium sulfate and calcium sulfate, both of these salt or both of these compounds are present in one solution. So everything is going to ionize in that particular solution, and the ionic strength, while calculating ionic strength, we have to consider all the ions produced by both of these salts. So if this is the solution, you have added sodium sulfate and also calcium sulfate. So inside this we are going to have obviously Na plus ions, SO4 2 minus ions, Ca 2 plus ions, and corresponding SO4 2 minus ions. So all these four of them will be present inside this solution, and we have to take considering all of them. So first step, again writing the ionization for first species here, that is Na2SO4. What will it form? There are two NAs, so 2 Na plus plus sulfate, so SO4 2 minus. The concentration of Na2SO4 is 0.01. So this concentration for Na plus will be twice of that, 0.02. For SO4 2 minus, the same concentration. Charge on this is plus 1 and this is 2 minus. Similarly, let's ionize calcium sulfate. CaSO4 on ionization will give Ca2 plus plus SO4 2 minus. So the charges are going to be 2 plus and 2 minus. Concentration was 0.02 for calcium sulfate. So this will be 0.02. This is 0.02. Again this will be 0.02. Now we need to fit all these four data into the equation for ionic strength. So I is equal to, what was the actual formula for I? Half into sum over I Mi into Zi square, which means you have to take the sum of all the species in here. So that will be, since I have like 4 species present here, they are like 1, 2, 3, 4. Just because the sulfate is common does not mean you have to take it once. Since the concentration is different, you have to take it both the times while calculating for I. So half into 4 species, so I would need m1 z1 square plus m2 z2 square plus m3 z3 square plus m4 z4 square. Okay, now let's write into or substitute for each of this. Let's consider so the species are, this is for Na plus, this is for SO4 2 minus associated with the Na plus, and this is for Ca2 plus, and this is for SO4 2 minus that came with Ca2 plus. So on substituting, M1 is 0.02 into Z1 will be, there is only one charge, so it is 1 square plus M2 is 0.01 for sulfate into Z square, charge is 2, so 2 square plus M3 is for calcium, the concentration is 0.02 into charge is 2 square plus M4 again concentration is 0.02 into charge is 2, so 2 square. So this will be half into 0.02 plus 2 square is 4, 4 into 0.01, 0.04 plus 2 square is 4, 4 into 0.02 will be 0.08 plus again 2 square into 0.02, 0.08. On summing all of this, we will get 8 plus 8, 16, 16 plus 4, 20 plus 2, 22. So that will be half into 0.22. On halving this, you will get 0.11. So this will be the ionic strength for a solution that contains this concentration of sodium sulfate and this concentration of calcium sulfate. So even if more number of compounds are added, it's just simple. Write the ionization for all the compounds, find their charge, concentration, and substitute into the main equation. So it's a simple question. You can do very easily, but you have to be careful while checking it out. Remember, it's always better to write this ionized form. So you might think this is not needed because you can just directly look into the question and answer this, but this is perfect so that you cannot make any mistakes from this. Okay, so that's it about ionic strength. So the next part is actually, you might be very familiar with, it is a Faraday's law of electrolysis. But before that, let's do a question on transport number, which is also relevant. So write down the next question. The ratio of ionic mobility of silver ion of Ag plus and NO3 minus is 0.75. Calculate the transport number of Ag plus and NO3 minus ions. That means you have to calculate the transport number for the cation as well as the anion, but the only given information is just the ratio of the mobility, ionic mobility of both of these ions. So first let's write what equation we know, or first let's write the data down. The only data given is the ratio of ionic mobility. Mobility we can represent it as U. So U plus by U minus. This ratio is given. Mobility of Ag plus and NO3 minus in that particular order if we take, it is U plus by U minus and their value is 0.75. Okay. Now let's write down the equation that we know. We know that the question is to find the transport number for Ag plus and NO3 minus. So transport number for Ag plus, which will be represented as T plus, this is going to be in terms of mobility. We know we can write transport number in terms of current, mobility and conductivity, but since this question is based on mobility, let's write with U. So T plus will be U plus divided by U plus plus U minus. And for anion, T minus will be U minus divided by U plus plus U minus. Since we do not know the value for U plus or U minus, but only their ratio, let's assume that U minus is equal to some constant x. In that case, we can write U plus in terms of U minus or in terms of x. So if it is x, what will be the ratio? It becomes U plus divided by x is equal to 0.75. And now writing U plus in terms of x will be U plus equals 0.75 into x. So we got that U minus is equal to x and U plus is 0.5 times x. Now it's easy, we can just simply substitute into this equation. The difficult part was just assigning values for that. So finding transport number of U plus. So transport number of cation, that is T plus. We know it is U plus divided by U plus plus U minus. So that will be, the value of U plus is 0.75 into x. So let's write it as it is. So 0.75 into x divided by U plus plus U minus. So 0.75x plus x. 0.75x plus x. That will be 1.75x. Right, 1 plus 0.75 is 1.75. So this is 1.75x. Now as you see, the x gets cancelled out. Okay, that is not an issue for us. The x will not be any issue for us now. It will just get cancelled out because we are taking the ratio. Now the ratio can be found by simply dividing the both values. So this will be equal to 0.429. So simply calculate this, the answer will be 0.429. So transport number, because you can see the numerator and denominator are the same value, both are velocity. So it is going to be a unitless quantity. It's just a number, as the name suggests, transport number. So it's a unitless quantity. That is in case of cation. Similarly, in case of anion, it is going to be simple. It will be U minus divided by U plus plus U minus. So what is U minus? It is x divided by 0.75x plus x. Already got that it is 1.75x. Cancelling out x just as before, what we have left is 1 divided by 1.75. What will be the value we get on calculating this? You get 0.571. Again, unitless quantity. So the question was simply to find the transport number for Ag plus and NO3 minus given a particular ratio. So the only task here was to assign a constant for U minus, or you can assign a constant for U plus also, but you'll have to do the changes accordingly. Okay, so that was a simple question on transport number. Now let's go into Faraday's law of electrolysis. So before going into Faraday's law, we need to learn exactly what is electrolysis. So you might all be familiar with the process, but I'll just briefly describe it here. So in case of electrolysis, as I told before, you will be supplying electricity externally. Okay, and we will be using electrical energy to make some chemical reactions happen. That means electrical energy is converted into chemical energy during an electrolysis process. So we will have two electrodes, which will be called as the cathode and anode again. Okay. So there is an external circuit connected to this. And we'll have an electrolyte solution. This electrolyte solution will contain both anions and cations. Okay, and since this is the positive side and this is the negative side, the one in positive side will be called as the anode and one on the negative side will be the cathode. Okay, so we know if there is cations and anions inside the solution, obviously these ions are going towards the electrode which has opposite charge compared to them, which means all the cations will go to cathode while all the anions will go to anode and get deposited at anode and cathode respectively. Okay, so during electrolysis the ions in the solution will get deposited on the respective electrodes. This is what is happening. If suppose you have more than one kind of ions present, okay, obviously we should have at least two kinds of ions, that is a positive and a negative ion. If there is more than one cation or more than one type of anion present, then which kind of anion or which type of cation should deposit will depend upon those ions reduction potential, okay, or their oxidation potential we can say. For example, I am considering the electrolysis of sodium chloride. So I will be having in sodium chloride, I'll be having Na plus and Cl minus ions. So since it is a solution of sodium chloride, we cannot say that the only ions present will be Na plus and Cl minus. What else will be there in a solution of sodium chloride? What other ions are possible? Okay, before that, if my solution is, if this is electrolyte used is molten sodium chloride. Okay, in case of molten sodium chloride, if we consider molten NaCl, then the only ions present will be Na plus and Cl minus. In that case, what happens? In that case, at anode, what will I have at anode and cathode? Anode is positively charged, so Cl minus, just opposite charge will go to anode, and at cathode I will be having, since it is negatively charged, I'll have Na plus, because the only two ions possible here are Na plus and Cl minus. But when I use solution, in the sense aqueous solution of NaCl, aqueous solution of NaCl, in that case not only Na plus and Cl minus but also the ions formed from water will also be a part of the reaction. So I will have Na plus, Cl minus, H plus, OH minus. All these four ions are possible. Now which will be reduced at cathode or which will be oxidized at anode will be different, because there is a competition between two cations and two anions. So the cation with higher reduction potential will get reduced at cathode and the anion with higher oxidation potential will get oxidized at anode. Okay, so if I write for anode and cathode, we know that when we compare Na plus and H plus, obviously the higher reduction potential is for H plus, which means at cathode reduction will happen for H plus and not Na plus. So H plus will get reduced into hydrogen gas. Therefore at cathode, instead of getting a deposition of sodium metal, you will be getting an evolution of hydrogen gas. Similarly for anode, either chlorine gas can evolve or oxygen gas can evolve. So oxygen has higher oxidizing potential or oxidation potential compared to chlorine. So here oxygen is going to be evolved. Okay, so O2 minus will go here. So more exactly, if you write, chlorine gas will be evolved here, sodium metal, oxygen gas and hydrogen gas. So chlorine gas, sodium metal, O2 gas and H2 gas. Okay, this is what is happening during electrolysis. Now let's see what is Faraday's law for electrolysis, and there are two laws. Okay, Faraday's proposed two laws for electrolysis. So firstly, Faraday's first law. Faraday's first law of electrolysis. So what this law says is that the weight of substance deposited, we have seen that during electrolysis there will be some amount of substance depositing on the electrodes, right? Either substance will get deposited or it will be evolving as a gas. So the weight of the substance deposited is going to be directly proportional to the charge passed to the solution. This is directly proportional to charge passed through the solution. Passed through solution. Okay. So if you write in terms of weight W, directly proportional to charge, let's call it as Q. But we know that Q is equal to current into time, right? So what we actually know that current passed is equal to charge divided by the time. So obviously Q is going to be I into T, current into time. So we can replace Q with IT. So W is directly proportional to I into T, current into time. So let's write what are the terms involved again. This is the charge, Q is the charge, I is the current passing, and T is the time. Okay. Now we need a constant here. So the constant we introduce here is actually Z, and Z is called as the electrochemical equivalence. So now the equation becomes W is equal to Z into I into T. This is the actual equation for Faraday's first law of electrolysis, where Z is called as the electrochemical equivalent. Z is electrochemical equivalence. Now we can further write another forms for all these equations actually. So the electrochemical equivalent Z can also be said as the equivalent weight per farad. So Z, which is electrochemical equivalent, is equal to E divided by F. Okay, which means electrochemical equivalent is equal to E represents equivalent weight. Equivalent weight. And F is farad. You know 1 farad is 96500 coulombs. So F is farad. So Z is equal to electrochemical equivalent by farad. Now this E, equivalent weight by farad, and this E can also be written as molecular weight by number of electrons. So equivalent weight is written as M by N, where M is molecular weight and N is the number of electrons involved in the process. Number of electrons involved. Okay. Now we are going to combine all of this equation and put it into the first equation we have got. So we will be getting one more equation for connecting W and Q. So W we have wrote it as ZIT, but Z we know it is E by F and E is M by N. So Z itself can be written as M by NF, and when we insert that into this equation, you will actually get W is equal to M, Z is M by NF, so M I T divided by NF. Okay, so this is the another equation or the expanded equation for Faraday's first law of electrolysis. So both of these equations are important. W is equal to ZIT and W is equal to MIT by NF. All the terms involved are clearly written here. Okay. So the next thing we're going to study is just the second law for electrolysis. So Faraday's second law. Okay. So what second law says is that when the same quantity of charge is passed through different electrolytes, suppose we are doing electrolysis for different kinds of electrolytes, but we pass same current through same amount of charge through all of them. In that case, the mass of different substance deposited at their electrodes, obviously each system will have their own electrolyte and electrode, and when we are giving the same amount of charge to all of them, the mass of the substances deposited on their respective electrodes will be the ratio of their equivalent masses. So I'll write this statement here. When same quantity of charge is passed through different electrolytes, then mass of different substances deposited at respective electrodes will be the ratio of their equivalent masses. Okay. So suppose we are carrying out electrolysis for a salt containing zinc and for another salt containing copper. Now if I pass same amount of current to both of them, the weight of copper deposited, the ratio of weight of copper deposited to weight of zinc deposited will be equal to the ratio of their equivalent masses. That means equivalent mass of copper divided by equivalent mass of zinc. So since both copper and zinc, if you consider same amount of charge is passed, that means same farad of current. So Z is equal to E by F. F is same means we can actually replace E with Z for both of them, right? That means if I consider Z1 is equal to E1 by F1, Z2 is equal to E2 by F2. If I divide this entirely and I have Z1 by Z2 now, but same amount of current is passed, so F1 is equal to F2. Cut them, so Z1 by Z2 will be equal to E1 by E2. Why we did this is because ECU by EZN can be replaced by ZCU by ZZN. Okay, so the ratio of their weight deposited at the electrode, whether cathode or anode, will be equal to the ratio of their equivalent weights or the ratio of their electrochemical equivalent. So W in here actually represents this represents weight of zinc deposited. So the one above will be weight of copper deposited, and E is equivalent weight. So this is what Faraday's second law says. So in today's class we have learned about transport number, ionic strength. These are simple problems where you can easily score marks. And finally Faraday's law of electrolysis, the first and the second law. Okay.